you all for having me. I'm going to tell you guys about renormalizing diffusion models, which is a project I've been thinking about since November with Jordan Cotler, who's in the back, who many of you know. And I'm going to tell you, I guess, about the sort of very natural question, which is whether there's a natural way of engineering a neural network so that whatever it learns the RG flow of a field theory, which is, so this maybe is, this is some theoretical component to this, there's some numerical component to this. And I've, over the past couple months, I dove a little bit into the numerics, and that's forced us to clarify a lot of interesting theoretical details. So I'll try to outline all of that for you today. I'm really would like to tell you that this paper is out, but instead it's sort of out in 0 of 1 days because of, over the past week, I think the Harvard Wi-Fi has repeatedly kicked me off for using Colab too much. So for some point it blocked me from google.com addresses, but no others. So, it's sort of, this is all kind of, stuff is, it's in a good place. So let me tell you about renormalizing diffusion models. I guess this is diffusion model day, so that's kind of fun. Which way do I click? Oh no.
No, it's okay.
Yes. So before I tell you about renormalizing diffusion models, I'm first going to quickly remind you of some basic equations. If you think about Brownian motions, that's a particle moved around by some kind of time and space independent Gaussian displacements, then its probability density evolves under the heat equation. So the Brownian motions SD is on the top right, and the heat equation is on the top left. So if the particle also has some kind of friction term, then that's some form of Langevin dynamics, friction-like term. Then the SD, that changes the stochastic differential equation to the one on the bottom right, and then the probability density will evolve according to a different second-order elliptic PDE, and there's some way of translating between these, which is fairly straightforward. But the thing to remember is that the sort of second-order elliptic PDEs that come from stochastic differential equations, they're all convection diffusion type, so they have some interesting special properties. So in particular, the way you go from the stochastic differential equation to the PDE is that, well, you need to figure out where, if you probability density is concentrated at one point at some time, which means you know where the particle is, then you see where it could go. So that's computed by this quantity on the bottom, which is the sort of the kernel of this linear transformation, this linear PDE. And then if you don't know where your original particle is, well, you just look at where it might go over all the different possible initial positions. So that's the sort of convolution. Okay, so that's how you relate the PDE to the SD. And in general, if you have just an arbitrary linear stochastic differential equation, then there's the Steiner-Fokker-Planck equation corresponding to it. Okay, so now you guys might know that Wilson and Polchinski, back when the stuff was kind of getting off the ground, noticed that some natural RG schemes can be sort of cast into they can be put into the form of an equation of Fokker-Planck type. So specifically, the one that they focused on was sort of like soft cutoff Wilsonian RG. So Wilsonian RG, usually you integrate all the high frequency modes sharply, but instead you can kind of integrate them a little more slowly. So you never integrate all the high frequency modes out completely, you just exponentially suppress them. And then, so lambda is supposed to be this cutoff frequency. So that's so that you get some equation describing this flow of this probability density of your possible fields. And so as lambda varies, that's the cutoff. So you're just going to parameterize it logarithmically, which is very natural. So, RG flows always give you some equation of this form, where you just get some complicated functional of your probability density. And so Polchinski showed that you can, in the case of soft cutoff Wilsonian RG, you can derive that equation from this equation. So this is an equation for the flow of the interaction term. So you write your, how the free part flows under a cutoff, and so you just need to specify how the interaction part of the action flows, and flows like this. And this looks sort of like the heat equation if you squint at it, because it's got some Laplacian term for the action, for the interacting part of the action, but it's not quite the actual equation for the probability density, right? Because this is like I take log and then I subtract some interesting quadratic form. That's this equation. But you can write an equation for the actual probability density, and interestingly enough, it turns out to be of convection diffusion type. And so what that means, going backwards from this previous finite dimensional argument, is that it corresponds to some kind of stochastic dynamics for your field. Okay, so this is, by the way, what the stochastic dynamics for your field looks like. So this is like, you have your field, and if you write your field in momentum space, then this is the kind of SD it satisfies here. Eta t is uncorrelated in momentum space and time white noise. And there's this cutoff function, the standard one you use, you just write it in here and you plug it into that formula. So that's what, this is an equivalent way. Well, this is, in a specific sense, which I'll explain in a second, equivalent to soft cutoff Wilsonian RG. Okay. So this might seem a little confusing, just to clear something up, because you usually think of RG as something which like strictly integrates out higher frequency modes. So it's a deterministic operation on your field, which then generates a flow of your probability density. But the point is, basically by an instance of the continuity equation, you can also find a stochastic process for your field, which induces the same flow for the probability density. And so if you computed correlators, which are quantities that only depend on the probability density functional of your field, they would actually evolve in the same way. So in other words, there's quite a number of cases where if you have some deterministic RG scheme, you can write a related stochastic RG scheme, which does the same thing. And this is sort of essentially one way of formulating Polchinski's observation. So it's an infinite dimensional analog of that. So in our work, we played around with these stochastic RG schemes and we tried to learn them. And I'll say more about that in a second. Okay, so any questions so far? Great. So now there's not just one RG scheme, there's a whole bunch of them. And I don't know how to classify RG schemes or define them, because it seems like you can call anything you want an RG scheme. But there's one natural class, which you can sort of try to define, which are all flows of this probability functional, which are of convection diffusion type. And then, okay, so these are not quite precise formulations, but you can make these more precise. They, on one hand, erase the information of frequencies in phi above some function of t. And on the other hand, they preserve all the correlators of functions of the fields which only depend on frequencies below this sort of cutoff rate, where f is something, basically a time reparametrization. And these sort of schemes you can basically classify using this Wegner-Morris-Wetterick equation. Any one of them is valid in the sense that it satisfies these axioms, and so universal quantities you should certainly be able to compute using any one of them, but they can have incredibly different numerical properties depending on the scheme. So when you want to use them, you might want to actually design the scheme pretty cleverly. I'll show you something about that in a second. And they also have, there's something interesting about them. This is how I got into this. They all have, because of this formalism, they all have some kind of formulation in terms of gradient flow of some relative entropy. And this is a nice way to at least write them down and think about them. It helps manipulate some of these equations, which can sometimes get a little bit confusing, at least to me. Okay, so here's a different RG scheme, which was, I learned about it from papers from Carosa's thesis. So it's very, very simple. You take your field and you noise it diagonally in momentum space. Here, eta t is still uniform white noise. So this is, if you looked at this in position space, this would, of course, just be like you take the Laplacian of your field and you add white noise. So this is an Ornstein-Uhlenbeck type equation. And the reason this thing turns out to also be of sort of this Wegner-Morris-Wetterick type, it satisfies all those axioms. It's, one checks that. And Carosa studied this particular scheme because if you drop the noise term, then this is like just the, the heat equation. And so people were very interested in using like, heat equations for your field in the lattice community as a method for scale setting. They call this the gradient flow. So there's some kind of, the reason Caressa was interested in this is sort of a completely different narrative where, there's this Wilson flow, which is somehow like for gauge theories, it's at first order, it's some kind of Yang-Mills gradient flow, and then it has some higher order corrections. And it's sort of clearly RG-like, but it wasn't really clear if it was an RG scheme in any formal sense. And Caressa's work clarifies the connection somewhat precisely, I think. So that's an interesting part of the history here. But if you take this equation, this is very easy to simulate, and you take it to apply it to a picture of a cat. We've all been learning, physicists really like cat pictures and maybe also Feynman quotes. And you apply it to the picture of a cat, it turns into noise. And so everybody here now knows that, there have been a lot of people who have been learning the reverse processes. And that was a nice way of generating cat pictures or pictures of your field. And so that kind of method for learning these inverse processes has been gone under the name of these diffusion models. So those, I'll very briefly review those because there's something interesting to say. What people do is they try to parameterize the score, which is the gradient of the log probability, i.e. the gradient, negative gradient of the action, if you think about it in this analogy. And you'd write down some forwards equation, which is some SD, and you require that it sort of has a known limiting distribution. Like you know P0, you know P infinity, you don't know the flow in between, but you know the dynamics. And then it turns out that if you know the score, then there's a backwards equation, which from P infinity will go back to P0. But that obviously depends on the dynamics and on P0. That's the two conditions. So the backwards equation is canonical in a sense, which I can explain if you want. And also there's a deterministic flow, which gives the same flow of distributions. And that's this sort of ODE form of the backwards equation. And to simulate any one of those, you need to know the scores of all the intermediate guys. So of course, if you know the scores of all the intermediate guys, then you can use these backwards equations to sample by sampling from P infinity and then flowing backwards by integrating an ODE. Okay, that's diffusion models in a nutshell. And there's one more thing to say about them, which is that you optimize some functional. And of course, the most natural functional to write down is KL divergence. But there's also this Fisher divergence, which is just the L2 error under the data, under the true distribution. The Q is the estimated distribution. It's the L2 error under the true distribution of the scores. And there's a bunch of relations between them. First of all, these are all forwards Fishers. These are all forwards KL divergences. Secondly, this Fisher, you probably want to integrate at least one of these over T to make sure you learn all the guys in between, not just the one at time 0. And then thirdly, if you know the flow of your SDE explicitly, then you can make sort of training with respect to Fisher divergences very efficient because by some basically integration by parts. So that's sort of helpful. So there's already a lot you want to actually know things about the SDE to make things work. And there's something that's worth knowing, which is that these are all kind of related quantities. Like these KLs are upper bounded in a natural way by weighted averages of these Fishers over different times. And so in some sense, these objectives are all equivalent, but you want to optimize the right one to have good numerical properties. But something to say is that these are all very different from the objectives people use in much of the normalizing flow literature, which is reverse KLs. The reason for this is because these are all basically expectation values of something under the true distribution. So you need samples from the true distribution. In physics, you just know the action, the log probability, but you don't have samples. So if you want to learn one of these things from like samples from Q4 theory, which I'll show you how to do in a second, what you do is you run your model, and then it's a terrible sampler. But then you like do some MCMC steps and do an MCMC correction. So now you have an approximate sample from your distribution. And then you feed that back in to compute one of these functionals to update your network. So it's sort of, that's the kind of procedure you would do if you wanted to learn the natural thing that you do once you realize this analogy is that you say, well, I'm going to rig a diffusion model we're going to rig the SDE, so it's it's a lattice version of one of these Wagner-Morris-Wetterick type SDEs, and I'm going to learn this process. But because you don't have data, like you don't have pictures of cats, you have to kind of dynamically generate samples, do MCM sequence corrections, and then use those to update your sampler. So that's an interesting difference from the most standard kind of ML setting. Okay. So that's some stories. So something to say. So of course, there's this difference between what people do in ML, where they have lots of cat pictures, and physicists, you have, I mean, I guess you have lots of lattice field theory samples already. It's in some computer, but you might as well generate them dynamically. But as Miranda was saying, there's people have been understood that it's completely natural. If you want to generate a high resolution cat picture, you should first generate a low resolution cat picture and then generate a higher resolution one conditioned on the previous one and so forth. That looks like RG, right? Okay, so that's kind of clear. In a formal sense, it is RG if you choose your noising process to be of a specific kind. That's a rigorous statement that you can make, I think. I mean, up to lattice errors, essentially. But there's a bunch of, because this is such a natural idea, ML people have been doing all kinds of, like this Caruso SDE was actually coincidentally investigated as a noising process in this blurring diffusion models paper. Also, terms in this SDE naturally correspond to field renormalizations. And then in practice, people have done things which are very complicated. And it's very interesting to try to maybe build a unified theory of these different methods. But people have been basically, if you want to, images clearly have multi-scale structure. So you want your noising process to be multi-scale in one way or another. And so, well, that's true in physics and in ML. So because the same equations have the same solutions, people have, been doing things that at least have formal analogies. And sometimes are inspirational practically. Okay, so that once you see this analogy, there's two potential things you can do. The first one is you can try to use physics intuition to give recommendations to people in machine learning. So we just heard a great talk about that. The second thing you can try to do is you can try to use this connection to build ML models for sampling from studying physical theories where the parameters mean something. So maybe they're interpretable, maybe you can use physics intuition to design them. And maybe there's some relation between the two, because if you try this, you'll learn a lot about like the way that physics intuitions actually work numerically in practice for these problems. So we thought kind of mostly about the latter. So one natural application is about sort of sampling and effective field theory. And then there's more speculative one, which I think would require a lot of tuning. You just sort of have some concrete proposals about like how to build variational ansatz for ground states of PFTs. So, we have this paper which we really want to say is out, where it has this long review of diffusion models for physicists and RG flows for ML people. And then it puts all these different studies these different SDEs, and it gives some recommendations for how to design them numerically. It shows that you can learn some of these flows for like V4 theory and free field theories. You can really build these ML models, and for physical quantities like estimates of the renormalized coupling, they seem to actually learn the flows. So that's the kind of thing that we did. So first, I want to say something interesting, which is this is a picture of two RG flows, and they're scaled so that the cutoff parameters are kind of moving at the same rate. So the top is this like Polchinski RG, the bottom is this Caruso RG. So they look extremely different. The Polchinski RG, you see, in one time step kind of has already removed almost all the high frequency modes in a like literal seeing sense. The bottom one doesn't quite obviously do so. But you can see that the first one is really doing what you expect because, well, you just like zoom into this initial segment from time 0 to time 0.2. Okay, the t is like log lambda minus log lambda. Remember that. But yeah, yeah. So that's like coarse graining.
When you say Polchinski RG here, you have some fixed function k that's doing the cutoff.
Yeah.
And can you remind me
just like the one that.
It's the one Polchinski used.
Yeah.
And can you remind me again? I know Caruso RG is this newer thing, and you're saying it's naturally stochastic. What's a simple way to think about it in canonical?
I mean, you're kind of flowing towards a free field theory, essentially. It's the most natural thing, or somehow like if you wanted to write down a time-independent Ornstein-Uhlenbeck process flowing to a free field theory, you'd write the Caruso RG.
Yeah, thanks.
Just
Yeah.
a detailed question. Like in Caruso RG, like in order to compute the physical quantities, we also need to do a kind of subsampling, like you plug in like a phi of bx instead of phi of x, right? Like do that kind of rescaling.
Yeah.
So is what I'm looking at after that rescaling?
So no, you are not. So if you did that, then, for example, you would know that Polchinski RG should not converge to something like this. Polchinski RG, if you do that, should converge to something like white noise. So here we haven't done that rescaling. But in the estimator, you can, so there's different, I'm going to address that in a second. There's basically two ways of dealing with this problem. And one of them is you try to modify your SDE so that it actually does this rescaling. And there is a way of doing that, but it has some numerical cost because you can no longer exactly solve for the kind of the propagation kernel. On the other hand, you can also incorporate, so there's an anomalous dimension, and then there's the kind of engineering dimensions. The engineering dimensions so you can incorporate those into the estimator, and the anomalous dimension you can also estimate. So I'm going to show you something now, which is, so this is a plot of lambda, but with the momentum renormalization ignored. So lambda should blow up because it's a marginal operator in phi4 theory, but the momentum renormalization is pretty big, so it looks like it's decaying, okay? And these two things, even though they look completely different, so this is a plot from here to there for both of these schemes. The lambda actually decays in relatively comparable ways. And yeah, you can, if you continued on, it would actually decay. It's like different by a factor of 2 in practice. So that's interesting. So then I'll show you just 2 basic numerical plots about learning the fact that you can actually, so one thing we found is that learning this Polchinski RG is pretty hard, at least in this form. And there's kind of an intuitive reason for that. You see it really, radically cuts off the support of the distribution to like the lowest possible couple of dimensions. But lambda actually flows quite slowly under the Polchinski RG. So if you want to like converge to a known distribution, you have to sort of keep flowing here all the way to like all the way there. But then if you learn a normalizing flow backwards, you have to take like a very low dimensional distribution and then spread it out. That's very difficult for a strict normalizing flow. You might be able to do it where like with more of a noisy kind of reverse process framework, but we didn't get to try that. The Caruso RG is just much more natural to like go for, the neural network architectures to go from pictures like that one to pictures like this one. As a final distribution is supported on a relatively higher range of dimensions. But when you deal with the kind of estimators for the physical quantity, you can account for that. Yeah.
Just ask, this is not necessarily an RG question.
Yeah.
There is this problem with adversarial data.
Okay.
Where you've got a classification problem and then you do some small quizzing
Mm-hmm.
and you end up with getting a different class.
Uh-huh.
I'm looking at these and it is tempting to imagine that if you did an RG step, you could avoid adversarial data.
Maybe, I don't know. I have that would be something to try. Yeah, I mean, I'm not familiar if people have tried that or not. It's certainly very natural. Okay, so this is just a picture of these sorts of schemes. But now, so this Caruso RG you can kind of learn. So this is here like m squared is negative, lambda is positive. So we haven't quite like magnetized the magnet. But you see that. So the red thing is the true flow. The blue thing is this like kind of renormalizing diffusion model. The green thing is the thing you kind of learn using forward scale. One thing I found quite surprising is that, I mean, maybe you didn't optimize it. I don't know if I optimized it like truly optimally, but the forward scale models are really good samplers. But if you actually look at how well they model the distribution without doing the MCMC correction, it's kind of hard to get it to really nail like basic physical quantities. So and that kind of makes sense. It should concentrate on the modes, but it's not really a great like log density modeler. While diffusion models are actually pretty good log density modelers. So it's sort of less, so this plot of the blue thing, this is not like I use my sampler to sample. This is like I flow directly and I never do an MCMC correction. That's sort of, it's measuring the difference between the learned distribution and the actual one in like a kind of physical way. So you can also kind of try to learn lambda. So yeah, the lambdas, these forward scale things learn. So this is an estimator for the renormalized lambda. It's a pretty natural one. They learn ones that they're not really accurate representations of the actual density, but they're still great samplers, the things that people have been doing. Well, yeah, so this is not like a super cherry picked run. Like really learning lambda is pretty hard once you start getting closer to the phase transition, but you can definitely improve on not trying to learn the RG flow. And so there's a lot of interesting things you can do with this. You can try to incorporate like field and space redefinitions into the SDE. So field redefinitions are easy. That's this term. Space redefinitions, it's an explicit SDE you can write down, but it's just less efficient to like train on. At least we haven't tried to make it efficient. But you can also incorporate this space redefinition into the estimator within some range of RGs up until the lattice is like too big, up until you basically zoomed out. There's a test for that too. So there's something that's interesting here. If you did incorporate the space rescaling into the flow, then what you would be running is you'd be running like a multi-scale adaptive sampling algorithm where you have a fixed lattice, but it represents like it kind of grows the actual. It's not like I've averaged out my field, like I've also zoomed it out. And that's sort of analogous, but kind of very different numerical take on what people have, like I saw these talk of Ryan Abbott, where you kind of have like sort of like a block spin hierarchy of normalizing flows. This is sort of like you do all of that on a fixed lattice. You could do that. And all this stuff is very sensitive to like really tuning the actual RG scheme. But because at least what meaningful RG schemes are, you can sort of do this and extract physical results after you've tuned your scheme. And it's always interesting to remember the score function, the gradient of the actions. You really learn the score function, that should mean something. Okay, so how much time do I have? 0 time. Okay, so I won't say very much here, but at least formally, because the ground state of a field theory, if you only have any ground state, it's basically the root of a probability function. It also flows under RG. So you could try to use this to do variational ansatzes, but we haven't tested it numerically. We just describe a method for testing it. So what can I say? Now, this whole story is extremely interesting. I kind of accidentally found out how many things it sits at the intersection of. On one hand, if you want to prove that like Glauber dynamics mixes in high temperature Phi4, then using these Polchinski PDEs is actually the best way of doing that. Maybe the second best way, is maybe using something very similar called stochastic localization, which people like Montanari have been going around saying is basically the same math as the math behind diffusion models. If you want to show optimal good sampling for spin glasses, people use also the same mathematics these days. All of this kind of is connected to this whole optimal transport story, which I kind of accidentally ran across because that's the way you prove stuff. And also we're going to hear a talk about the connection to Bayesian inference. And finally, this Caruso RG is somehow connected to this gradient flow, like Wilson flow story. And I know people in the lattice community know a lot about that. I don't. I've just tried to read the literature, so I'd love to understand more about how people think about that. Okay, so I'm going to end with some dreams. One thing that would be great would be to infer the effective action of a field theory. And if you formulate, in RG, if you like train a diffusion model where the actual process is interpretable as an RG scheme, then you should be able to do that by, you can't learn the effective action, but you can learn its gradient. A lot of stuff is contained in its gradient, like its critical points are related to phase transitions, the sort of critical manifolds are related to Goldstone modes. So it'd be really great to check that this works for some simple field theories, that you can really learn the effective action and therefore start doing it's a very, if you want to learn the bare coupling corresponding to some renormalized coupling, you have to tune stuff a lot. Now here, okay, it's still expensive, but maybe if you do it for a whole bunch of parameters at once, then it starts becoming worth it. You can obviously train these RG flows to kind of learn a single parameterized flow for a bunch of bare parameters at once. Miranda sort of had a very nice, not Miranda, I'm sorry. Yes, it's had a very nice paper based on some of those ideas. And if you know that the score is meaningful, then you can start implying a lot of physical design principles. Like, you can add on a gradient phi or term, and that definitely improves the performance. All right, so I just want to say that this code that I showed, the neural network architecture was based on Miranda's previous paper, just to say it was not optimized at all, except for maybe these phi4 terms. Thank you.
Great. We already got some questions.
Thanks for the great talk. Can you please remind me again the quantity on the machine learning side, the neural network side, that corresponds to the momentum scale on the field theory side?
I think we do this. So I don't know if there's there's two ways of thinking about this. One is that maybe there's some kind of general dictionary between physics intuitions and ML intuitions. The other one is that when you apply ML to a specific context, if you design your model correctly, then parts of your model become physical. So, I don't know how to answer that question in our case, because it is the momentum. We have these pictures, and you look at their Fourier transform, and then you can diffuse in that space. That is it's just the same thing. So I don't know how to answer it beyond that.
Yeah, so in this sense, isn't your momentum scale unidirectional?
What?
You're coarse-graining out some of the degrees of freedom here,
Yes.
which corresponds to momentum.
Yes.
And once you coarse-grain them, can you exactly reconstruct back where you started from? Can you go back to the original point? Can it traverse the direction of that flow?
You can learn the backwards flow of the distributions, at least reasonably well. I've been trying to show that this is possible for simple field theories.
Yeah. Okay.
That's what these plots are about. Right. So this is, lambda effective. So, this is a measure of the non-Gaussianity, and it's a quantitative measure of the non-Gaussianity of the distribution you've learned. And you're supposed to get a correct number for this measure in the physical context.
Okay. The training time, does it have any corresponding variable on the field theory side?
The training time, no, not to my knowledge.
Okay, thank you.
The amount of t here, well, this is not the training time, right? This is the time you flow by. That corresponds to different scales. T is minus log lambda. But that's not related to the training. I didn't show any training plots. Obviously, how the ESS and how these different metrics change as you tune your diffusion, or the functionally optimized are quite sensitive to that.
Okay, thank you.
Yeah, thanks a lot for the great talk. Apology for the super technical question. So on the plot, so RG flows are notoriously hard to compute. So how do you get the red curve? Like the ground?
So just doing averaging processes is pretty efficient, right? And then there's, these red curves are pre-explicit. So this is like a reasonable estimator for the correlation length. And then, it's like a kind of fairly common one. And you can, it's just the estimate of the correlation length under the flow of this SD. Of course, you can, estimate the anomalous dimension as well once you know this and so forth. And so that's how you can compute the correct version of lambda. So this is like lambda where I've put in the anomalous dimension, but I have not put in the momentum rescaling, because the momentum rescaling causes it to get really large, which is what should happen for a marginal operator that's whatever, the opposite of marginal. Yeah. More questions?
Maybe just one comment for your question. If you just take an individual sample from the UV theory and then you just stochastically flow it, that's how you get the samples in the IR. Maybe I'm not sure if that's what you're asking.
Right. So there's this question of like, what's the correct amount of space rescaling to do and so forth, right? And I mean, in the case of phi4 theory, you kind of know enough about that to, I mean, there you just, yeah, I mean, I can explain in complete detail if you want. Okay, more questions? Yes?
So here, the coarse graining is compared to the RG flow of 5.4. Have you tested this connection to any other kind of interaction terms in phi? Derivatives of phi, for example?
So, I mean, yeah, so we thought about it. We haven't tested it. It's kind of natural to, so, you know, a really good test would be, so we know that phi6 should be irrelevant in 3D. So you should, you know, do all this in 3D and then really see that. That's, I mean, of course, people know that that's true on lattice, so it has to work. But yeah, we did not, you know, in 2D because all the operators, because operators are not like by default irrelevant. We didn't test anything. Yeah.
Okay, so the expectation is that it should work.
I mean, I think so. In higher dimensions, learning the flows of many operators, because many of them are irrelevant, should be easier because you just need to get them to die. In 2D, things should be relatively complicated potentially.
Okay, thank you.
Any other questions? All right, let's thank our speaker again.
All right.